Hello everybody and welcome back to the next installment of our EZC tutorial videos. Today we are going to be talking about smart tasks and how they help with autonomous movement. And it'll kind of incorporate the integrated motor encoder, but in reality won't have too much effect on that. That'll still have to make a separate video. Alright, so as every program you should ever do, either import an existing controller configuration or really quickly set up yours. I just grabbed the RecBot one. I'm not actually going to be showing the effects of the program today just because I don't have my camera with me, but I'll explain to you what each of these functions should do. Alright, I probably should have taken care of this before. Readme.text. Basic for smart control. As we've discussed in previous videos, you always write something, some sort of info in your readme.text so that your program can be identified, verified, and explained, and put any feedback if you're giving, or for other teams, and for you to put instructions for your program. I discussed that in our first video, Intro to EZC. Alright. So, in your function blocks window, there will be, all the way down here, a window that says Smart Tasks. In this, there will be 3 subfolders: Motor Module, Robot Driving, and Wait Until. Okay, we're going to just cut to the chase with the integrated motor encoders and just jump right into it. So, with your motor time controls and your multi-motor time controls, Smart Motor Control and Smart Multi-Motor Control, you can set a motor to run, so left drive, to run at 127, so that's full counterclockwise, I think, maybe. I don't have it memorized. For an amount of milliseconds, which can be defined by a variable such as if you were going to use a timer. For now, we'll just put 1.5 seconds. And it's as simple as that. The motor will run clockwise for 1.5 seconds. Your multi-motor control allows you to do the same exact thing. So you can select how many motors are being controlled, up to 4 motors from 2 to 3. So if I were to say 1 to 10, and then invert the direction of 1, and then 127 again. So 1 being my left drive, 10 being my right. For that right there, set both my motors to run. And because I inverted 1, it should run forward for 1.5 seconds. And then obviously I'd comment, I'm not going to bother doing that because I'm about to delete it. Right, delete. Now we actually move on to use our integrated motor encoders. The Smart Motor Control allows you to, instead of saying you can have 2 different criteria for how it's going to move. In rotations, so how many rotations do you want your motor to go? Which, if the Smart Motor Control is definitely best for your movement, because you're going to have your IMEs, or integrated motor encoders, on your movement patterns. And so, obviously, basic physics, you know that each rotation of the wheel is going to travel the distance of the circumference of the wheel. So if you know that with the 4-inch wheels, you're going to move, I'm not going to do the math, 4 pi, or 2 pi r, no, it's, okay, 2 pi squared, that's it. Or 4 pi, same difference. You can you can travel that distance and you can just measure it out and say, okay, if I'm going to go this distance, so x distance divided by 4 pi, uh, that'll show you how many rotations you need, and maybe you need 3.27 rotations, so you put that in, and it will rotate 3.27 degrees, assuming that you have your integrated motor encoder programmed in. And in order to have that, you're going to have to see in your configuration, you're going to have to note that it is a IME. So motor port 1 description. So IME left movement. I don't know why I capitalized that. And it will only work if you have it noted that it has the integrated motor encoder and what motor port it goes to. Or else none of that will work. It'll just kind of not work, or just it won't function at all, and it will act as a break in the program. And again, same thing for smart multi-motor control, in which you can detect how many motors are being controlled. So 2, 3, 4. The power, and then the degrees or rotations. The degrees would be better for, say, an arm like we have with the rec bot. I need it to move up 90 degrees. I need my motor to move counterclockwise 90 degrees in order to be perpendicular to the floor. So that's where that would come in. After that, we have what's best used for robot driving, which is conveniently marked robot driving. Before any of this stuff can work, you have to first define your motors. So you just drag your defined motors in, and you determine which one is your left motor, which one is your right motor. And then up here, you need to know which motor is your master motor. So if I'm going to put in 127 for my left motor, and my right motor is not inverted, my right motor is going to run at negative 127, because your left motor and your right motor should run at inverses of each other. This can be messed up if you have the motor controllers, because if you don't put red to red and black to black, this can screw up with your 2 wires, which are your 393s and your 282s. Convenient. Just minus 1 from each. And so if I put it as my right motor, it's going to make my right motor my master motor. And I can also adjust that I have 4 motors versus 2 motors. It's weird. When I first did this, it had a little diagram of a base bot, or a square bot there. And then comment defines motors. Really should have nothing more than that ever. And then from there, you can just put drive, power 127, enter. As simple as that. You don't have to mess with your motors. You don't have to consistently input what motors you're doing. So this will drive forward or backwards. I don't know, depending on how your robot is built, and so what value you put into here. And so you can, instead of having to put each motor and what way it's going, you can drive it in a curve so that it's going to slowly turn as if it were following a circle, or the circumference of a circle. You can turn it from the center so it's going to remain stationary in displacement, but it's going to rotate, because that's just how motors drive. You can turn swing, so this is going to turn dependent on the power that you put in here. It's going to either stop your left motor and run your right motor, so the robot is going to swing itself around, hence turn swing, or turn off your right motor, move your left motor. And then in order to stop, stop that. And there's nothing more to put to it, so hi. Usually your comment would be something like stops movement. And that just eliminates the need for you to have to have just long strings of motors and wait commands, because after that we have the same thing, except now it's with timed controls. So I can, just as I did with drive, I can say move forward, so 127, oh, whoops, for however long I need it to be. So value we've been using all episode, I shouldn't call these episodes, that sounds gross, all video, 1.5 seconds, or 15,000 or 1500 milliseconds. So that will run it forward. That'll drive the robot forward for 1.5 seconds and then stop it. Hence why there's no stop time control, because you don't really need that. And so each of the drive curve, drive center, drive swing will do the same thing as they do up here, except with that added time control. Now we have our smart motors drive, which again uses our IME. And for that you have to have that notation that there is an IME, an integrated motor encoder on your config page, which that's really the only time it's useful for actual programming purposes, like affecting the robot's programming, not just being incredibly helpful. And so rotations, degrees, we already talked about the difference between that. Degrees says, okay, do X amount for X time. And this still works with the defined robot motors, and you have to do that in order to make it work. All right. So again, smart motors drive curve, or turn center. It doesn't have a turn swing, but realistically, your turn center is going to be better for navigation on a field anyways. All right. So now that we've talked about all that, let's end it off with, well, we're not going to end it off. We're going to make a sample program. And if you're paying attention, this is the autonomous challenge that I'm doing, or that I'm making my kids do for the October-November challenge. Cough, cough, wink, wink, pay attention to this part. Or to the next part, not this part. Well, do pay attention. These wait until. So I shouldn't use a bumper switch. I'll use a limit switch. The wait until limit switch will act as a break in the program, or a pause in the program, until the conditions that is here, so these condition settings, have been met. So the program will not proceed until the condition below has met. So it acts as a stop in the program until you finish with, or this condition is true. So input is equal to 1. So that means the limit switch, the program will not work until my limit switch is pressed. All right. So, and that's just the same thing with every sensor. We don't have an accelerometer or a gyro sensor, so don't worry about that. You should be independently learning how to program all these sensors on your own. I'll make a video on that sometime soon. I'm not going to have that out for a while. And then your integrated motor encoders are same thing, except for with your integrated motor encoders. For the robotics kids, you guys don't get these until competition time, so you really oughtn't worry about it. Digital and analog inputs can be edited in your digital and your inputs. So analog input, digital output. So those, and then high resolutions. You shouldn't worry about that for the purposes of robotics. You'll rarely use those ever. They are helpful though. Alright, so now that we've kind of explained what all these things do, let's write a quick program with them with the knowledge that we've accumulated over these past couple videos. Alright, so the autonomous challenge for the October-November challenge is to drive the robot in a square. To drive the robot in a square inside the arena. So what's something that obviously we want to use our robot driving, and so how are we going to repeatedly do, or how are we going to drive forward, turn, and then repeat that same action over and over again? Drive forward, turn. The best logical choice here is a for loop, so we're going to create a count variable, integer x, value of 0. Enter. Count variable. Always remember underscores are better than spaces. For loops. So add variable x equals 0. So that initializes our program saying so long as x equals 0, as x equals 0, as we just defined in our variables, conditionalizes it, so x is less than or equal to 3. So that'll make sure that it runs 4 times because 0 is inclusive because of our less than. And then our finalizer, so what's our condition here? Add variable x once again, and then plus plus. That'll add a value of 1 to our value, or to the value of x, thus meaning that it's 0, 1, 2, 3, 4 total loops. All right, loops the program 4 times. All right, so now we need to define our motors. Mine are 1 and 10, with my master motor being left. Really quickly, I'm going to adjust this back to being standard so it doesn't affect my program at all. I'm going to define my motors outside my for loop because do I need to put the stress on my brain to define it 4 times? No, I do not. In my for loop, I'm going to drive time control. So I know, or actually, no, I'm not going to use a sensor. I'm going to let you guys figure that part out for yourself. Have fun. I'll explain it in a future video. Don't worry. Cough, cough. Use the wait until. So, 127. So forward. For, let's say, at the speed of my motors, my gear ratio, and my wheel diameter, say that I'm going to move at 15 inches a second. That's fairly fast. Not even going to lie. And my robot, or my field, is 185 inches, calculator, long. So let's assume I start 4 inches into the arena, so 185 minus 8, because I don't want to hit the edge of the arena, equals, and then we're going to divide it by 15, 11.8. So you need to run for 11.8 seconds. That's not correct math. What did I just do? No, that's right. So you need to run it for 11,000 and then 800. So 11.8 seconds. Enter. Then I need to stop. Or no, I don't need to stop because I'm using a time control. And then from there, I want to turn center time control. power 127, so that means my opposite will be running at negative 127, and left being my main, that means my right motor is going to run at negative 127, my positive 127, or a half turn, that's going to be what? 12 inches, so 12 divided by 15. As a mathematician, I'd like to pretend like I knew that off the top of my head, but I don't. So 0.8 seconds, duh, that was obvious. So 800 milliseconds long. And this is just a rough guesstimate, so this means I'm going to be turning my center for 0.8 seconds, enter. And so now I have gone forward, and I have turned a 90-degree angle. And so in order to drive a square, I'm going to have to do this 4 times, hence my for loop. And so now that I have done this, my robot should be done. So what I'm going to do after I finish programming it, I'm going to clean up my program. So comment defines motors for movement. Notice how, since I'm using the motor defines motors, I'm capitalizing. Yeah, that's just proper. Here, drives robot forward for 11.8 seconds. Enter. Enter. Turns robot leftwards 90 degrees. Enter. Alright, so now I'm going to, I would then do trial and error, download my program in, and test it out in my arena. And then if I need any editing from there, I would do said editing. Once I'm done with that, we're going to go to our Project Explorer, readme.txt, and then enter C, or I should probably call it hex coding. And then I'm going to have the really fun act of writing all of this as it is in the same format. So right here. So I'm not going to make you guys sit as I type the whole thing out, but that's what you would do in a real program. So include main.h, and then you type all that out, and hopefully that's so that you can start to understand the hard coding of all this stuff. But that if you're part of any affiliations like I am, I'm affiliated with Greenway Robotics, Greenway Robotics. Alright, and so that should be the end process of your program. So you would save it and make a few copies of it across several different accounts so that your partner can use it as well. No, I want to bring my main back over here. And so there you are. You're done with your program, and I hope you all have a fantastic day.